Hello, my name is Gabriel. I'm a PhD student from the University of East London, and I'll be presenting today about a new suspended sand concentration model for breaking waves. This presentation is based on the findings from a research paper authored by myself, Dr. Ravindra Jayaratne of the University of East London, and Professor Tomoya Shibayama of Waseda University. Long-term morphodynamic modelling is difficult as naturally occurring processes are non-linear and occur over large areas over many years. Many modelling techniques have been developed over the years. These include 2D, quasi-3D and three-dimensional process-based models, one-line models, data-driven models, hybrid and reduced physics models, etc. Previously in existing literature, process-based models were thought to be unsuitable for long-term morphodynamic modelling due to the inherent practical and theoretical limitations. Practical limitations generally refer to computational costs, and theoretical limitations refer to process insight and robustness of constituent models. In recent years, practical developments such as MORPHAC and theoretical developments such as clearer process understanding has led to major advances in process-based modelling for medium to long-term morphodynamic modelling. Even with major developments in the last few decades, there are still numerous areas that require continuous research and development, both with regards to practical and theoretical limitations. An example of theoretical limitations that still require our attention is the lack of robustness and accuracy in sediment transport models, particularly in the breaking and swash zones. Improvement in accuracy and applicability of such sediment transport models could lead to improved performance in morphodynamic models by incorporating the improved transport models into morphodynamic modeling suites such as Delft3D, MIKE21 and Telemac. This could also enable the wider implementation of process-based morphodynamic models to medium to long-term problems. As such, the objective of the present study was to evaluate the performance of existing sand transport models formulated for breaking wave conditions and to derive a new model that accurately predicts suspended sand concentration under breaking wave conditions. Here you can see a table providing a brief overview of the 4 datasets used in this evaluation study. The first dataset is from the Large Installation Plan Programme, referred to as LIP, collected in the Delta Flume at Delft Hydraulics. The second is from the Crosstex project, collected in the OH Hinsdale Laboratory at Oregon State University. The third and fourth datasets are from the SANTI Pro and SIMBAD experiments, collected by the same group of researchers at the CIEM Flume at Polytechnic University of Catalonia. All datasets were collected in large flumes with mobile sand beds, with average grain diameter ranging between 0.22 to 0.25 mm. All datasets had a breaker bar situated in the breaking zone. The LIP and Crosstex datasets were measured under irregular breaking waves with 2 different test conditions: erosive conditions, which had shorter wave periods and are predominantly spilling breakers that lead to erosion; accretive conditions, which have longer wave periods and are predominantly plunging breakers that led to accretion. The SANTI Pro and SIMBAD datasets were measured under regular breaking waves with strong plunging breakers. Using the 4 datasets described in the previous slide, 6 existing reference concentration models were evaluated. For the sake of brevity, not all 6 are covered in this presentation, but further information about the existing models tested and detailed analysis can be shared upon request. The performance of these models was tested for the shoaling, breaking and inner surf zones under regular and irregular breaking wave conditions. This is because a sediment transport model that is only adept for one cross-shore zone is of little use, practically speaking. In almost all existing C0 models, substantial underprediction was found, particularly around the wave plunging point where strong increases in concentration was induced by large-scale breaking-generated turbulent vortices. This is elaborated more in the next slide. In particular, models that were driven mainly by the wave climate or local water depth performed poorly, especially in the breaking region. Also, formulations driven mainly by bed shear were adept in replicating the measured concentration in the shoaling zone but not in the breaking zone. This is because these formulations did not take surface-generated breaking-induced TKE into account. Here on the left-hand side we can see comparison plots between computed and measured reference concentration as a function of the cross-shore coordinates. The bottom panel shows the initial and final bottom profiles, indicating significant bar development over the test period. Here x equals 0 is at the wave paddle, in other words the seaward end of the flume, and z equals 0 is at the surface. Notice the breaking point is around x equals 53 meters, plunging point at x equals 55.5 meters, and the splashing point at around x equals 59 meters. The center plots are the main plots of interest, as they show the measured reference concentration, the red triangles, versus the computed reference concentration. Now the plots on the left with the yellow markers indicate that the computed values were computed using the formulae of Mock and Smith 1992, and the ones on the right with grey markers were computed using the formulae of Van Rijn 2007. Both models can be seen to show relatively good agreement with measured data in the shoaling zone between x equals 51 to 53 meters, and the inner surf zone between x equals 59 to 63 meters. But in the braking zone, particularly near the plunging point, there are very large discrepancies. This trend was observed to varying extents in all tested existing models. On the right hand side, we can see the computed values against all 72 cases from the Sinbad dataset. In both cases, we can see large percentage of points lying outside the factor 2 region. The root mean square error was also very large. Such large discrepancies can accumulate when computing sediment transport rates, resulting in unrealistic morphodynamic predictions. As such, it is essential that an improved concentration model is developed for use under breaking wave conditions. Latest studies indicated promising relationships between the near-bed turbulent kinetic energy, or KB, and reference concentration C0, providing an alternative method of modeling the reference concentration. This alternative method is the direct implementation of KB values, measured or modeled. The issue with this approach, however, is that KB-driven models are highly dependent on the accuracy of measured or modeled KB and are also sensitive to the magnitude of KB. Now, as KB is very difficult to measure and or model accurately, the slightest errors can have significant effects on the resulting concentration values. Even the variations in the magnitude of KB between different datasets resulted in varied performance of such models. As the fruit scale TKE produces smaller deviations in magnitude of TKE between datasets, it is suggested that the use of the fruit scale TKE in concentration models may be more suitable than using KB. Overall, the greatest limitations of existing C0 models can be summarized into two categories. Number one, they are not adept for multiple cross-shore zones, for example the shoaling, breaking and inner surf zones. Or number two, they are incapable of replicating localized high values of suspended sand concentration found in the breaking zone. In order to address the common limitations of existing concentration models, a new C0 model, referred to as L19, was derived based on the novel empirical relationship between C0 and the inverse water depth. It was found that the cross-shore distribution of C0 was inversely proportional to the cross-shore distribution of the local water depth, and therefore it was used as one of the driving parameters of the new L19 formula. Some of the benefits of using the inverse local water depth is that it incorporates the effects of bathymetric changes over time, the breaker bar position and development, and also the breaking intensity. The reference concentration was also found to be a function of the sediment properties, wave climate, entraining and settling forces, and more. Therefore, key parameters such as the average grain diameter, wave climate, gravitational acceleration, and roller energy dissipation were also incorporated to account for effects of sediment pickup and settling forces. Detailed explanations on the choice of parameters used, validation and calibration of constants have been omitted in this presentation for brevity, but can be provided on request. Here this figure elaborates on the key relationship between the inverse water depth and C0. The bottom plot and middle plots are similar to those seen in previous slides, showing the bottom profile evolution and cross-shore distribution of measured concentration respectively. The top panel shows cross-shore distributions of the wave height, breaker height, water depth, and the inverse water depth. From this we can see that as the measured C0 increases near the plunging point, the wave height and water depth decrease considerably, whilst the breaker height stays stable. This indicates that these parameters are not suitable to be used as driving parameters for the C0 models. As mentioned earlier, some existing models were driven by the wave height and or the water depth, hence their poor performance in the breaking zone. Alternatively, however, it can be seen that the inverse water depth mirrors the cross-shore distribution of measured C0. This of course is not coincidental, but can be explained by the presence of the breaker bar. Near the breaker bar crest, where breaking generally occurs, is where concentration begins to increase due to the breaking-induced turbulent kinetic energy. The bar crest where concentration is highest is also where the local water depth is lowest. At the bar trough, where water depth is highest, the breaking wave has already plunged and the wave energy dissipated, hence the decline in measured concentration. Based on the inverse relationship between C0 and the water depth, and also the incorporation of key parameters such as the wave climate, grain diameter, and gravitational acceleration, the following formula was derived. 13 out of 119 test cases were used to calibrate the omega constant. The purpose of the omega constant was to enable the use of the L19 model in multiple cross-shore regions. As mentioned before, one of the major limitations of existing transport models was that they were not adept for multiple cross-shore zones. The implementation of the omega constant was a simple and effective solution to overcoming this limitation. Following the same method used for evaluating the existing models, the newly proposed L19 model was evaluated against measured data. The new model was found to perform very well, indicating good agreement with measured data in all three cross-shore zones. Even against the cross-text dataset, which had irregular spilling breakers, the performance of the L19 model was very good. The root mean square error when tested against all 119 test cases was also marginal, ranging between 0.36 to 1.79 kilograms per meter cubed. In summary, existing C0 models covered in this study were found to be incapable of accurately replicating the cross-shore distribution of suspended sand concentration in multiple cross-shore regions. In particular, they performed poorly in the braking zone, near the plunging point where braking-induced turbulent kinetic energy induced highest concentration. A new model was proposed for use in multiple cross-shore zones and was proven to be adept, even under strong plunging breaker conditions. The new L19 model showed very good agreement with measured C0, with root mean square error ranging between 0.36 to 1.79 kilograms per meter cubed over 119 test cases from different datasets collected under regular and irregular wave conditions. The simple L19 formula requires little calibration and is well suited for all tested cross-shore regions, unlike alternative models. Future studies will be focused on integrating the L19 formula into morphodynamic modeling suites such as Delft3D. Finally, the authors would like to acknowledge the University of East London, who partly funded this research under the UEL's Excellence PhD Studentship Scheme. The authors would also like to acknowledge Worcester University as collaborators in this project. A special thanks is given to Joop van der Zanden of the Maritime Research Institute, Netherlands, for sharing experimental data and invaluable comments and insights for the presented research. The authors would also like to thank Ad Roniers of TU Delft, Daniel Cox of Oregon State University, and Hyundog Yoon of Myongji University for sharing the datasets with the authors. Finally, the authors would like to thank Harshini Karunaratne of Swansea University and the two anonymous reviewers whose comments helped to improve the manuscript upon which this presentation is based. Here is the list of references, and I'd like to thank you all for your time and for listening to our presentation.